Welcome back to the Snoozy Scientist, a calm corner of the universe where curiosity and science drift together to put you to a calm sleep. Tonight, we're slipping beneath the waves into a world that feels so near to us and yet remains almost entirely unknown. The ocean covers more than 70% of our planet, a shimmering blue expanse that defines Earth from space, yet we have seen vanishingly little of it. While high-resolution sonar has mapped just over a quarter of the global seafloor as of mid-2025, direct visual observation of the deep ocean floor remains less than 0.001%. 123. The rest is a vast blank space, unmapped, unobserved, and unexplored. Even with satellites orbiting high above, even with our most advanced sonar and robotic explorers, most of what lies beneath remains a mystery. We know the surface of Mars with greater clarity than we know our own seabeds. 4. To put it in perspective, only a handful of people have ever reached the Challenger Deep, the deepest place on Earth. That's fewer than those who have walked on the moon. And down there, the rules of our world collapse. At just 1,000 meters, the last rays of sunlight vanish forever. Beyond that lies a night so complete it has lasted for millions of years. And yet somehow, impossibly, life thrives down there. Strange creatures that defy everything we once believed about how life should work. Entire ecosystems built not on sunlight, but on volcanic fire. With every dive, explorers return with forms of life we have never seen before. The ocean holds mysteries that remind us how little we know of our own home. Most of our ocean is still waiting to be discovered, but the haunting truth is that we may never be able to explore it all. Not because we lack curiosity, but because of the challenges. So why can't we truly explore the ocean the way we dream of? What stops us? Even in an age where we have built rockets that escape our own atmosphere and sent robots to other planets. And why is the ocean, our own home, still humanity's greatest unknown? Tonight, we'll descend together into the dark side of the ocean to see what we know, what we don't, and why the sea may always hold secrets beyond our reach. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's mysteries, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. I do hope this story soothes you toward rest. Now, take a deep breath, close your eyes, let your shoulders soften, and let's begin. When we look up at the night sky, the stars feel impossibly far away, yet strangely familiar. Through the lenses of telescopes, we can see the faint glow of galaxies, billions of light years distant. We can trace the structure of swirling nebulae and measure the size of worlds that orbit stars far beyond our own. Space feels vast, but it is also transparent to us. Its mysteries are laid bare for collection, one by one. 5. What is astonishing, though, is that our ability to study these distant places often surpasses our ability to study what lies beneath the waves of our own oceans. The reason begins with the very nature of light and water. Satellites soaring high above Earth can send radar beams across continents and deserts, mapping mountain ridges and river valleys with extraordinary accuracy. They can capture the craters of the Moon and the canyons of Mars in remarkable detail. But when that same signal, a pulse of electromagnetic energy, meets the ocean, it falters. Water swallows light. It bends radio waves and it scatters sound. To a satellite, the ocean is a shimmering shield, hiding everything beneath its surface. What satellites can do is measure the height of the water itself, with incredible precision. Where there is a massive underwater mountain or seamount, its gravity pulls the water towards it, creating a subtle, invisible bulge on the surface. Conversely, a deep trench creates a slight dip. By measuring these tiny variations in sea level, we can infer the hidden shapes of ridges and trenches deep below, giving us a rough outline of the seabed, a sketch in broad strokes. It is how we know the general shape of the Mariana Trench or the Mid-Atlantic Ridge. Yet the detail is blurred, like looking at the shadow of a mountain rather than the mountain itself. When astronomers use space telescopes, they are peering into distances so vast that the numbers hardly seem real. Light traveling for billions of years still finds its way to our detectors. We can map the structure of the universe across time itself. In contrast, when oceanographers try to map the deep sea, they face limits that arrive within a few short kilometers. Sound, not light, is the tool of choice underwater. Ship-based sonar sends out pulses that bounce back from the seafloor, and by measuring the echo's return time, researchers can estimate depth and shape. Yet, the ocean is immense, and sonar must be used painstakingly, ship by ship, across vast stretches of water. Even then, sound waves weaken with distance, and the deeper the ocean becomes, the harder it is to hear what lies below. What we end up with are fragments of maps, narrow corridors of detail, stitched together over years, while the majority of the seabed remains a mystery. Consider Mars, a planet tens of millions of kilometers away. Through orbiting spacecraft, we have high-resolution images of its entire surface. We can trace ancient riverbeds, measure the height of dormant volcanoes, and study the dust storms that sweep across its plains. Mars is barren, cold, and distant, yet we know it more intimately than the living seas of our own planet. Earth's seabed, by comparison, is patchy and incomplete. This paradox captures the heart of the problem. Outer space, though unreachable for ordinary travel, is transparent to our instruments. The ocean, though it laps at our shores, remains stubbornly opaque, and so we find ourselves in a strange position. We have mapped the red deserts of Mars in sharp relief, yet we cannot say with confidence what lies beneath the waves just off our own coasts. It is this contrast that makes the ocean feel even more mysterious. The cosmos offers us a view, however distant, but the sea holds its secrets close. What we know of it are glimpses, shadows, and fragments, hints of landscapes and life forms that remain concealed. And as we move from this question of visibility into the deeper realities of the ocean itself, we must confront the barriers that lie not just in the limits of our instruments, but in the very nature of the deep. Because beyond the issue of mapping lies a greater challenge. The abyss itself, with its crushing pressure, its freezing cold, and its eternal darkness. The deeper one descends beneath the waves, the more the familiar rules of our world begin to unravel. What seems serene at the surface hides conditions so extreme that they test the limits of human engineering and imagination. Every meter down adds a new layer of challenge, an invisible weight, a creeping chill, a deepening shadow, until the ocean becomes not just a body of water, but a vast fortress defended by pressure, cold, and darkness. The first of these guardians is pressure, an invisible force that grows heavier with every step into the abyss. At the surface, we live under the gentle press of one atmosphere, the weight of the air above us, a force so constant we never feel it. Yet for every 10 meters of depth, the ocean adds another atmosphere of force. By the time one reaches 1,000 meters, the body is already facing 100 times the pressure felt on land. To go deeper is to invite forces so immense they can crush steel and shatter glass. At the bottom of the Mariana Trench, the pressure is equivalent to the weight of 50 jumbo jets stacked one on top of the other, pressing down on every square inch of a vessel's hull. This is why submarines designed for deep exploration are so unlike the graceful vessels of fiction. They are not sleek but shaped like spheres, because a sphere distributes pressure perfectly, leaving no weak points. Their walls are thicker than bank vaults, forged from layers of solid steel and titanium. Even then, every descent carries an almost unbearable risk, as the smallest crack or weakness could mean instantaneous, catastrophic implosion. The Trieste, the first vessel to reach the Challenger Deep in 1960, had a viewing window made of plexiglass nearly 7 inches thick. During its dive, that window cracked with a deafening bang, a reminder that even the strongest designs are fragile when confronted with the weight of the deep. This pressure does not only challenge our machines, it transforms the very fabric of life. Creatures of the abyss have evolved cell membranes reinforced with unique proteins and small organic molecules called piezolites, which prevent their cellular machinery from being crushed. Their bodies often contain no air-filled cavities, like lungs or swim bladders, that could collapse. For them, the pressure is not a danger, but a constant, the baseline of their world. For us, it is an almost insurmountable wall, separating our realm from theirs. Cold is the second guardian, creeping in long before the trenches are reached. Even in shallower depths beyond the reach of the sun, the water temperature falls rapidly. At a few hundred meters, the warmth of the surface gives way to a near-freezing chill. The average temperature of the deep ocean hovers just above 0 degrees Celsius. A cold so steady and so ancient, it has shaped entire ecosystems. For humans, such temperatures mean hypothermia within minutes. For our machines, the cold is a silent saboteur. It slows electronics, hardens lubricants into sludge, and turns every moving part brittle. Batteries that would last for hours on land are sapped of their energy in minutes. Life here has adapted in strange and beautiful ways. Many deep-sea animals have slow metabolisms, conserving energy in the cold. Some produce antifreeze-like proteins that prevent ice crystals from forming in their blood. Fish and invertebrates drift in near stillness, their survival depending on patience and efficiency rather than speed. The chill preserves the deep as a kind of natural archive, where the bodies of great whales and the wrecks of lost ships can remain intact for centuries, their stories frozen in time. For explorers, however, it means every mission must be equipped with powerful heating systems and insulation, just to keep equipment functioning against the silent freeze. Then comes the barrier that defines the abyss more than any other: darkness. Sunlight, that great enabler of life on Earth, fades quickly in water. At a few hundred meters, only a faint blue shimmer remains. By 1,000 meters, the last photon of sunlight vanishes forever. Beyond this twilight zone lies an eternal night that no human eye has ever fully adjusted to. Here, the only light is made by life itself. Flickers of bioluminescence glowing in the black, or the brief, invasive flash of an ROV's lamp as it drifts across the seafloor. This darkness is more than the absence of light. It is a realm where evolution has chosen strange and wondrous paths. Many deep-sea creatures have eyes that are enormous compared to their bodies, wide lenses designed to capture even the faintest spark. Others have lost eyes altogether, adapting instead to a world perceived through vibration, pressure waves, or faint chemical trails carried on the slow currents. For humans, darkness strips away our most fundamental sense, leaving even the most advanced submersibles dependent on instruments rather than vision. The ocean floor here is mapped by sonar pings and the dim glow of artificial lamps, never by natural sight. To face all three barriers together, pressure, cold, and darkness requires a level of engineering that borders on the impossible. Every descent into the deep demands not just a vessel strong enough to endure the crushing weight, but also systems that can withstand freezing temperatures and navigate a world without light. Even then, the ocean resists us. Voyages are rare, costly, and brief. For the most part, the abyss remains untouched, a reminder that the sea does not give up its secrets easily. Yet, it is precisely these barriers that give the deep its aura of mystery. Each time we try to descend further, we are reminded not only of how harsh this environment is, but of how much life has already adapted to it. For every wall that seems unbreakable to us, creatures have found a way to thrive, turning the abyss into their home. Far beneath the rolling waves, hidden from the reach of sunlight and the warmth of the surface, the seafloor drops away into vast chasms that cut into the very crust of the earth. These are the deep ocean trenches, some of the most extreme and least explored places on our planet. They are not merely valleys, they are scars left behind by the colossal, slow-motion violence of tectonic forces, where one great plate of Earth's crust slides inexorably beneath another, pushing rock downward into the molten mantle. The result is a wound in the planet's surface, a feature of staggering scale, stretching for hundreds of kilometers and plunging to depths greater than the height of the world's highest mountains. The most famous of these is the Mariana Trench, lying quietly in the western Pacific Ocean. At its deepest point, a small basin known as the Challenger Deep, the seabed sinks nearly 11 kilometers below the surface. To truly imagine this depth, picture Mount Everest, the tallest mountain on Earth, inverted and placed within the trench. Even then, its peak would still be swallowed by more than 2 kilometers of water pressing down from above. It is a place so remote and so hostile that only a handful of humans have ever seen it with their own eyes. The first attempt came in 1960, when the bathyscaphe Trieste, a vessel more akin to an underwater balloon than a submarine, carried Jacques Picard and Don Walsh into the darkness. Their descent lasted nearly 5 hours, a slow, creaking journey as the tiny crewsphere contracted under unimaginable pressure. When they finally reached the bottom, they glimpsed a flat, serene plain of diatomaceous ooze, a fine silt stirred by their landing. Through a small, thick porthole, they reported seeing life even there, a flat, soul-like fish moving slowly in the gloom, a defiant spark of existence in a world that should have been utterly barren. Then, after just 20 minutes, they began their long journey back upward, leaving the seafloor as untouched as they had found it. It would take more than 50 years before another human returned. In 2012, filmmaker James Cameron descended alone in a custom-built submersible, a craft he called the Deep-Sea Challenger. It was a strange, vertical vessel, a tall, narrow torpedo designed to slice through the water column and withstand the crushing forces of the trench. He spent hours exploring, gathering images and samples that revealed a barren but hauntingly beautiful world of fine, gray sediment. Yet his dive, like the one before it, covered only the tiniest fraction of the trench, a single pinprick of light in a vast, dark abyss. Since then, only a few more dives have been made, often by experimental vessels or privately funded missions. The number of people who have visited Challenger Deep is still fewer than the number who have walked on the moon. Each descent is a monumental feat of engineering, requiring vessels with walls thicker than vault doors, systems to withstand freezing cold, and instruments that can function in total, absolute darkness. But the Mariana Trench is only one among many. There are more than 20 known deep-sea trenches around the world, from the Tonga Trench in the South Pacific, which plummets almost as deep, to the Puerto Rico Trench in the Atlantic. Many of these are nearly as deep as the Mariana, yet most remain entirely unmapped and unexplored. They are immense gashes in the Earth's surface, hidden beneath miles of water, holding landscapes as dramatic as the highest mountain ranges. Steep cliffs, winding valleys, and towering geological formations lie there unseen and untouched. What little we know of these trenches often comes not from direct observation, but from the ghostly echoes of remote instruments. Deep-towed sonar has revealed hints of strange shapes, while robotic submersibles have captured brief, fleeting images of otherworldly creatures drifting in the void. Giant amphipods the size of human hands, translucent snailfish with fragile, gelatinous bodies, and microbial mats clinging to rocky walls have all been found in these depths. Yet every expedition returns with more questions than answers. The scale of what remains unseen is overwhelming, as if we are staring at a door that has only been opened a fraction of an inch. These trenches are not only biological frontiers, but geological ones. They are the active boundaries of tectonic plates, where the Earth reshapes itself in silence. Earthquakes often rattle along these lines, and devastating tsunamis are born in their shadows. For now, they remain like distant rumors, places that belong to science fiction as much as to science fact. And so, even though the ocean surrounds us, the truth is that its deepest places are still beyond our grasp. We have only skimmed the surface of these immense abysses, barely touching their edges, while their vast interiors remain cloaked in mystery. For as long as humans have sailed the seas, there have been whispers of strange beings rising from the depths. Sailors told tales of tentacles as thick as tree trunks wrapping around ships, pulling them into the black waters below. For centuries, these stories lived in the space between fear and imagination, dismissed by many as myth. And yet, in recent years, we have learned that the truth was not so far from the legends. The giant squid, once a creature of maritime folklore, has been confirmed to exist, not in sailors' tales, but in flesh and blood, a titan of the deep with a body stretching over 12 meters and eyes larger than a human head, the largest in the animal kingdom, designed to capture the faintest glimmers of bioluminescent light in its dark world. These animals remind us that the ocean has always kept its secrets well. For most of history, we never saw them alive. What little we knew came from carcasses washed ashore or scarred fragments hauled up in fishing nets, and from the circular sucker marks branded onto the skin of sperm whales, evidence of titanic battles fought in utter blackness miles below the surface. It was only in the early 21st century that cameras finally captured a giant squid in its natural home, gliding silently through the midnight waters like a ghost. Even now, so much of its life remains a puzzle, its behaviors hidden from us in the abyss. The giant squid is not alone. The deeper one goes, the stranger the ocean becomes, as though each layer is another universe entirely, governed by different laws of physics and biology. Down in the abyss, where light has never reached, creatures have been forced to adapt in ways that defy our expectations. Their bodies are shaped by the extremes of pressure, cold, and perpetual night. Many are translucent, their forms ghostly and delicate, the ultimate camouflage in a world without shadows. Others are slow-moving scavengers, masters of a zen-like existence, conserving energy in a world where food is scarce, where the fall of a single whale carcass from the sunlit world above is a gift of manna from heaven, feeding entire communities for decades. Every dive into these depths reveals something new. Remote operated vehicles, or ROVs, have allowed us to glimpse into the abyss more often than humans themselves ever could. With cameras, mechanical arms, and bright lights, these machines drift down where pressure would crush steel and where the cold can freeze most forms of life. And each time they descend, they capture images of animals never seen before. Scientists have estimated that the majority of species in the deep sea remain undiscovered. Our knowledge is like a single candle lit in a vast, dark cathedral, illuminating only what is directly before us, while the true scale of the space and what else it contains remains in shadow. Some of these discoveries are both beautiful and unsettling. There is the famous anglerfish, the female, a patient hunter in the void, dangling a glowing lure from her head to draw prey into her gaping, needle-toothed mouth. Stranger still is her method of reproduction. The male is a tiny, parasitic creature who, upon finding a female, bites into her flesh and fuses with her body, his own organs withering away until he becomes little more than a permanent, living sperm bank. There is the goblin shark, a living fossil whose lineage stretches back 125 million years. With its pale pink skin and a grotesque, protrusible jaw that shoots forward to snatch prey, it looks more alien than earthly. And then there is the vampire squid, a creature whose name belies its gentle nature. It drifts through the oxygen minimum zones where few other animals can survive, and when threatened, it pulls its webbed arms over its body like a cloak, turning itself inside out to reveal harmless, fleshy spines. For every strange creature we catch a glimpse of, there are countless more that vanish back into the darkness before we can study them. The challenges of observing these beings mean that we often know only fragments of their stories. A fish seen for a few seconds on a camera might never be encountered again. A sample drawn from the depths may not survive the journey to the surface long enough for us to understand its way of life. It is humbling to realize that even in an age of satellites and global networks, the most abundant habitat on Earth is still a frontier of myth. The ocean cradles millions of years of evolution, shaping bodies and behaviors that have never been witnessed by human eyes. Somewhere in the black corridors of trenches and the sweeping plains of the abyss, there are creatures so strange they may challenge our very ideas of what life can be. The ocean is often described as the silent world, but in truth, it is anything but. Beneath the surface, as light surrenders to darkness, sound becomes the dominant force, the primary language of the deep. Waves breaking, whales singing their ancient, complex songs, the crackle of a million snapping shrimp, and the low groan of currents rushing against the seafloor all merge into a hidden symphony that fills the dark waters. Unlike light, which fades after only a few hundred meters, sound travels astonishingly well in water. Low-frequency noises, in particular, can be channeled into a deep layer of the ocean known as the SOFAR channel, or the deep sound channel. Here, a unique combination of temperature and pressure creates a perfect acoustic waveguide, trapping sound and allowing it to travel for thousands of kilometers with very little loss of energy. It is a hidden highway of sound, a planetary-scale communication network that life, and our own technology, has learned to use. It is here, in this realm of echoes, that some of the most mysterious signals ever recorded have been heard, captured by a network of underwater microphones that were never intended to listen for the planet's secrets. Originally laid down across the Pacific Ocean during the Cold War, the U.S. Navy's sound surveillance system was a web of hydrophones designed for one purpose: to detect the faint acoustic signature of Soviet submarines. But when the Cold War ended and scientists were given access to this secret network of ears, they began hearing things no one could explain. One of the most famous of these is known simply as the Bloop. It was detected in the summer of 1997, a powerful, ultra-low frequency noise that rose rapidly in pitch and was so loud that sensors more than 5,000 kilometers apart all picked it up. At first, no known animal could explain it. Blue whales, the loudest living things on Earth, did not produce sounds with such a rapidly changing frequency, and the sheer volume of the bloop seemed impossible for any known biological source. For years, the mystery lingered, sparking speculation that perhaps there were giants in the deep, creatures far larger than anything we had ever seen. The truth, when it came, was just as awe-inspiring. Many scientists now believe the bloop was the sound of a massive iceberg cracking and breaking away from a glacier in Antarctica. It was the sound of ice, not a monster. But the legend of the bloop remains, because in the ocean, the line between explanation and enigma is never truly clear. Not long after, another strange signal was given a name. It was called Julia, a long, mournful moan recorded in 1999 that lasted for nearly 15 seconds, echoing through the Pacific. Like the bloop, its source was eventually traced to a large iceberg running aground off Antarctica, but one could not shake the eerie impression that it resembled a cry, as though the ocean itself had sighed in its sleep. Then came Upsweep, a name given to a repeating series of long, rising tones, first detected in 1991. Upsweep has been heard seasonally ever since, usually strongest in spring and autumn, but its source has never been definitively identified. Some have proposed volcanic activity, as it seems to originate from a region of underwater seismic unrest. Others still suspect a biological origin, some unknown rhythm of life we have yet to encounter. Upsweep continues to puzzle researchers, a signal without a clear sender. There are many more, scattered across decades of listening, whistles, groans, bangs, and hums that appear suddenly in the hydrophone recordings and then vanish without warning. These ghost sounds remind us how little we know of the ocean's interior. They reveal just how powerful sound is beneath the sea. While on land, it is light that defines our sense of space. In the ocean, it is vibration, echo, and resonance. Each unexplained sound leaves a trace of wonder, because in a world as vast and hidden as the sea, any signal might belong to something we have never encountered. The bloop, Julia, Upsweep, and countless others are not just noises in the dark. They are reminders that the ocean is alive with voices, some familiar and some forever beyond our reach. In the deepest waters of the ocean, where sunlight has long since vanished and darkness stretches without end, there is still light. But this is not the familiar, warm glow of a star. It is a cold fire born from life itself. It shimmers and pulses, flickers in silent waves, and dances across the bodies of creatures that seem as though they belong to another world. This is bioluminescence, a phenomenon so widespread and yet so mysterious that scientists are only beginning to understand its full, silent language. Bioluminescence is not rare in the ocean. In fact, it is the rule, not the exception. The deeper you go, the more life glows. In the abyss, the majority of animals are thought to have some form of it. It is created through a near-perfect chemical reaction inside the body, where a molecule called luciferin reacts with oxygen, often triggered by an enzyme named luciferase. The reaction releases energy not as heat, but almost entirely as light, a cool, efficient glow that is often blue or green, wavelengths that travel farthest through seawater. To those who witness it, the effect is almost magical. Yet it is entirely natural, honed by evolution over millions of years into a sophisticated toolkit for survival. The uses of this living light are as varied as the creatures themselves, a complex vocabulary in a world where sight is otherwise impossible. Some use it to hunt. The anglerfish, drifting patiently in the black, dangles a glowing lure from a filament on its head, a single, hypnotic point of light. Small prey, curious or fooled by the glow, drift closer until the predator snaps its jaws shut. Others use bioluminescence as a shield. When startled, some squid and shrimp release clouds of glowing ink, a photonic bomb that confuses attackers and gives the prey a precious moment to escape into the blackness. One of the most ingenious defensive strategies is what scientists call the burglar alarm. A small creature, when caught by a predator, will flash brightly, not to scare its attacker, but to attract the attention of an even bigger predator, effectively screaming for help with light. But perhaps the most subtle use is for camouflage. In the twilight zone, where a faint glimmer of sunlight still filters down from above, many animals employ a technique called counter-illumination. They have light-producing organs on their undersides that they can adjust to perfectly match the faint blue light from the surface, effectively erasing their own silhouettes and making them invisible to predators looking up from below. It is nature's own Klingon cloaking device. For all this, the most fascinating uses of bioluminescence may be found in its role as a secret language. In the darkness, vision is limited, so animals use light to communicate. Flashing patterns can signal readiness to mate, mark territory, or help members of the same species recognize one another. Some deep-sea shrimp flash coded bursts of light, while lanternfish use glowing patches on their bodies like identification tags. And then there are the true masters of this light, like the stoplight loosejaw fish. This creature has evolved one of the most remarkable tricks in the deep sea. It can produce red light in an environment where almost all life sees only in blue and green. Red light is effectively invisible. The loosejaw, however, has also evolved the ability to see its own red light, giving it a secret sniper scope beam that it can use to illuminate prey without ever being detected. What is striking is how much we still do not know. For many species, the exact reasons for their light remain uncertain. Why do some jellyfish flash in patterns so complex they seem almost designed? Each discovery raises more questions. The wonder of this light is not confined to the very deepest seas. Even in coastal waters, on warm nights, swimmers sometimes leave glowing trails with every movement as clouds of tiny plankton respond to disturbance. Waves break in bright streaks along the shore. Small echoes of the vast light show hidden far below. To think that in the total absence of the sun, life has created its own form of day, its own constellations in the dark, is both humbling and extraordinary. Bioluminescence turns the deepest ocean into a shifting, glowing theater where survival, communication, and beauty all take place in silence. Between the sunlit shallows, the world we know, and the eternal night of the deep, lies a realm unlike any other on Earth. Scientists call it the mesopelagic zone, but it is more poetically, and perhaps more accurately, known as the twilight zone. It stretches from about 200 meters below the surface down to nearly 1,000. Here, light does not vanish all at once, but instead thins into a dim and ghostly blue glow. Sunlight filters down faintly, just enough to blur the outlines of shadows, yet never bright enough to sustain the green of plants. It is a place that is neither day nor night, a shifting, liquid boundary that is home to some of the most elusive life on the planet. The twilight zone covers a vast expanse, encircling the globe like a hidden belt of mystery. Though invisible to us at the surface, it is immense, containing more living biomass than all the world's rainforests combined. Within its shadowy waters swim countless fish, squids, and gelatinous creatures, many of which have never been captured or studied. Their shapes are tuned to the gloom. Some, like the hatchetfish, have sleek, flattened, silver sides that reflect the faint light, making them shimmer and vanish into their surroundings. Others are a deep, velvety black, their bodies absorbing every last photon and rendering them almost invisible against the blackness beneath them. Many carry their own lanterns, small points of bioluminescence that flash and flicker like stars in a liquid sky. Every evening, as the sun sets and darkness blankets the ocean, the twilight zone comes alive with the greatest migration on Earth. In a synchronized, planet-wide movement, billions of fish and invertebrates rise from these depths toward the surface. It is a mass movement so vast that it can be detected by sonar, forming a thick, deep scattering layer that fooled early naval operators into thinking it was a false seabed rising and falling with the sun. By day, these creatures remain hidden in the deep, safe from predators. By night, they rise to feed on the rich plankton near the surface, their shimmering bodies following the ancient rhythm of the planet. This daily journey, repeated again and again, may involve more animals than all the herds and flocks on land combined. Yet for most of history, humanity never knew it was happening. The creatures that live here are masters of light and shadow. Many have enormous, tubular eyes tuned to capture the faintest hints of blue light, or upward-facing vision to spot the silhouettes of prey above them. Others use counter-illumination, glowing on their undersides with an array of photophores that they adjust to perfectly match the faint sunlight filtering down from above, a sophisticated form of active camouflage that makes their outlines disappear from view. For all its abundance, the twilight zone is still almost entirely unexplored. Its depths are too deep for satellites to see, but too shallow for many deep-sea submersibles to linger. Nets brought up from this zone often crush or kill the delicate, gelatinous animals they capture, leaving us with fragments rather than whole specimens. What we know comes from fleeting glimpses, from short expeditions, and from the shadows caught on sonar. In truth, we have studied only a fraction of this immense habitat. Yet what little has been learned suggests that the twilight zone may play a critical role in the balance of our planet. When its creatures rise at night to feed, they consume carbon-rich plankton at the surface. When they return to the depths by day, they carry that carbon with them, actively transporting it away from the atmosphere in what is known as the biological carbon pump. This vertical transport, repeated every 24 hours by billions of animals, helps regulate the climate itself, acting as one of the planet's great, unsung lungs. To drift into the twilight zone is to enter a dreamlike place suspended between light and dark, a realm of enormous abundance, yet also one of profound invisibility, tucked just out of reach of human eyes. In the late 1970 seconds, a team of oceanographers lowered a submersible into the dark waters off the Galapagos Islands. Their mission was to explore a section of the seafloor that lay along a mid-ocean ridge, a place where the Earth's crust was slowly pulling apart. No one expected to find anything extraordinary. The deep ocean was thought to be a barren, biological desert, a place where life could not possibly survive without the energy of sunlight. Yet, in 1977, when their lights illuminated the seafloor nearly 2.5 kilometers down, the world of science was transformed forever. What they discovered were not just geological formations, but entire, thriving ecosystems, clustered around fissures in the Earth's crust, where superheated, mineral-rich water was bursting forth from beneath the planet's surface. These were hydrothermal vents, underwater chimneys, some rising as tall as buildings, spewing dark, billowing clouds into the water. And around them, to the astonishment of the scientists, was an oasis of life. Giant tube worms, some 2 meters long, clustered in dense colonies, their bright red plumes swaying in the shimmering currents. Clams the size of dinner plates covered the rocks, and strange, pale crabs scuttled across the vent openings. It was a revelation, a community of life existing entirely without the sun. For all of Earth's history, as we understood it, photosynthesis was the foundation of every ecosystem. That without the sun, there could be no food chain. Yet here, in the crushing darkness and near freezing temperatures of the deep, life had found another way. The secret was chemistry. The water erupting from these vents was rich in hydrogen sulfide, a compound toxic to most animals. But at these vents, specialized bacteria had evolved to use it as their energy source. Instead of photosynthesis, which relies on light, they performed chemosynthesis, building sugars and sustaining themselves entirely on chemical energy from the Earth's interior. These bacteria became the foundation of the vent ecosystem, living in symbiotic partnership with the tube worms, clams, and countless other creatures that had adapted to thrive in this seemingly impossible environment. What had once seemed a desert was in fact a cradle of abundance, all powered by the Earth's inner fire. This discovery of life, powered by geothermal energy, not solar energy, raised profound questions about the origins of life itself. If life could exist here, thriving in complete darkness and under pressures unimaginable at the surface, then perhaps the very first forms of life on Earth had not emerged in a sunlit, warm little pond, as Darwin had speculated, but in the dark, mineral-rich cauldrons of hydrothermal vents. These vents provide not only energy but also shelter, with mineral-rich chimneys forming complex microenvironments where the building blocks of life could gather and react. The idea stretches even further. If Earth's ocean can host such thriving ecosystems without sunlight, then perhaps other worlds could too. Moons like Europa and Enceladus, orbiting far from the Sun, are believed to have liquid oceans hidden beneath thick shells of ice. If hydrothermal vents exist on their seafloors, as many models suggest, then life might not be limited to Earth alone. Chemosynthesis could be the universal answer to survival in places where the light of a star can never reach. Despite their richness, hydrothermal vents remain fragile. The same mineral deposits that make them so unique have attracted human interest, particularly in the emerging industry of deep-sea mining. But these ecosystems are often ephemeral, sometimes lasting only decades before shifting or collapsing as the planet's plumbing changes. To disturb them could erase communities we barely understand and species we have not yet discovered. What is most striking about hydrothermal vents is the reminder that life is not limited by the rules we once thought were absolute. They remind us that the ocean's mysteries are not only about strange creatures or unreachable depths, but also about the very story of life itself. When we look beyond Earth, past the swirl of clouds and the blue curve of our own oceans, we find other worlds that seem barren and hostile at first glance, cold, airless moons circling giant planets, their surfaces frozen solid. Yet beneath their crusts of ice, in the deep, silent dark, scientists now believe there are hidden seas. And in these alien oceans, the discoveries made in our own abyss have found a profound and startling echo. Europa, the bright, scarred moon of Jupiter, is one of them. Cracks and reddish fissures stretch across its icy surface, signs of a dynamic world being constantly stretched and squeezed by the immense gravity of its parent planet. This tidal flexing heats its interior, and beneath those fractures lies an ocean that may be more than 100 kilometers deep, containing more liquid water than all of Earth's oceans combined. Enceladus, a smaller, brilliant white moon of Saturn, offers its own, even more dramatic evidence. In 2005, the Cassini spacecraft flew past it and discovered towering geysers erupting from its south pole, great fountains of water vapor and ice crystals shooting into space. These plumes come from a global ocean beneath its crust, warmed by the same friction of tidal forces. And when Cassini flew through these plumes, its instruments detected not just water, but salts and simple organic molecules, the very building blocks of life as we know it, being offered up freely into the cosmos. What makes these discoveries so haunting is how much they mirror the lessons learned from our own deep world. On Earth, beneath crushing pressure and in total darkness, hydrothermal vents pour out heat and minerals, creating habitats where life thrives without sunlight. If such environments exist on the seafloor of Europa or Enceladus, then they may host their own ecosystems. Chemosynthesis, the same process that powers life at our own vents, could be a universal strategy. The blueprint is already here, hidden in our own oceans, demonstrating that a star is not a prerequisite for life, only a source of energy, and a planet's own inner heat can serve just as well. But if the oceans on our own planet remain mostly unexplored, how can we hope to uncover what lies beneath the ice of distant moons? On Earth, we have only touched the edges of the abyss. Now imagine the challenge of sending a probe across hundreds of millions of kilometers, landing it on a frozen surface, drilling through kilometers of ice thicker than any glacier on Earth, and then releasing a submersible into a sea we cannot see. The complexity is staggering, and yet the possibility pulls at us like gravity itself. When scientists study Earth's deep seas, they are not only learning about our planet, they are, in a very real sense, rehearsing for journeys beyond it. The strange microbes that live on chemicals instead of sunlight, the ghostly fish that drift in the twilight zone, and the creatures that glow with living light all teach us what is possible in worlds cut off from a sun. Each expedition to a hydrothermal vent or a polar sea on Earth is a glimpse into conditions that may exist on Europa or Titan. Our own ocean becomes a living laboratory, the only model we have for imagining life elsewhere. These alien oceans stir questions that feel both scientific and deeply human. Could life exist in places so far removed from the warmth of a star? Would it resemble the creatures we know, or would it take forms beyond anything we have ever conceived? If we one day send a submarine beneath Europa's crust, will it drift past glowing shoals of plankton-like beings, or find only barren rock swept by silent currents? The answers lie hidden, waiting in waters that may have been undisturbed for billions of years. The dream of reaching these oceans is one of exploration at its most daring. It asks us to go not only farther than we ever have, but deeper than we have ever managed. And it reminds us that what we discover in our own oceans does not only belong to us, it may be the key to recognizing life when we finally encounter it beyond our world. The mysteries of the deep sea and the mysteries of the stars are bound together, reflections of the same enduring question. What does it mean for a world to be alive? For centuries, sailors spoke of them in hushed tones, stories traded in the dim light of taverns after long, perilous voyages. They told of monstrous waves that rose out of calm seas without warning, walls of water taller than any ship, that would strike with such sudden, absolute force that entire vessels were swallowed whole, leaving not a splinter of wreckage behind. On land, these accounts were passed down as sea stories, often dismissed by scientists and naval architects as exaggerations, the wild imaginations of weary travelers, or a convenient excuse for errors in navigation. For a long time, these rogue waves were regarded as myths, belonging to the same realm as sea serpents and phantom ships. Yet, in recent decades, the ocean has revealed that these invisible giants are terrifyingly real. On New Year's Day, 1995, a single, colossal wave struck the Dropner oil platform in the North Sea. The seas were rough, but nothing out of the ordinary, until a vertical wall of water, an almost impossible shape, rose from the churning gray. Instruments on the rig recorded its height at over 85 feet, towering higher than the platform itself. The wave came out of nowhere, more than twice the size of the waves around it, and it matched the very descriptions that sailors had given for centuries. This was the first time such an event had been captured with precise data, and it forced the scientific community to reconsider the stories they had once dismissed as folklore. Since then, satellites scanning the surface of the oceans with radar have confirmed that rogue waves are not rare accidents, but regular visitors, roaming the seas silently. A rogue wave can rise more than 100 feet high, taller than a 10-story building. Unlike tsunamis, which are born from seismic events, rogue waves form suddenly in open water. They are the ocean's perfect, deadly storm, created when the random energy of smaller waves, driven by winds and currents, aligns in just the right way. Through a process called constructive interference, their energies stack, one on top of the other, focusing the power of a wide stretch of sea into a single, towering, liquid mountain. Their lifespan may be short, a few terrifying moments, but their impact is enormous. A ship caught in the path of such a wave can be torn apart before a distress signal is even sent. Some of the many vessels reported lost in fair weather, without clear cause, may have been victims of these sudden walls of water. Yet rogue waves are not the only giants the ocean hides. Even more catastrophic are megatsunamis, events so rare and so violent they defy comparison. Unlike ordinary tsunamis, which already carry unimaginable power, a megatsunami can rise to heights beyond 300 feet. These are not triggered by shifting plates beneath the seafloor, but by sudden, colossal displacements of water. A massive landslide crashing into a bay from a coastal mountain, a volcanic island collapsing into the sea, or even an asteroid strike can generate waves that tower over coastlines. One such event occurred in 1,958 inches Alaska, when a massive earthquake triggered a landslide that sent 90 million tons of rock plunging into Lituya Bay. The wave that followed was a force of almost geological scale. It scoured the landscape clean, stripping trees from slopes more than 700 feet above sea level, the highest wave ever recorded on Earth. The terrifying thought is that these forces still exist today. The Cumbre Vieja volcano in the Canary Islands has been studied as a potential source of a future megatsunami. A catastrophic collapse of its flank could send a wave across the Atlantic, striking the eastern seaboard of North America with devastating effect. While the likelihood of such an event in our lifetimes may be small, the possibility remains. A reminder that the ocean holds powers beyond even the worst storms. What ties rogue waves and megatsunamis together is their profound invisibility until the moment they arrive. A calm sea can conceal the seeds of chaos, energy building silently beneath the surface until it converges into a single, towering wall. For those who witness such an event, there is little warning, only the sudden, horrifying appearance of water rising higher than imagination allows. Not all mysteries of the ocean are hidden in its deepest trenches, nor are they all born of natural forces. Some of the most unsettling are found much closer to the surface, spreading quietly beneath the waves. They are not creatures or unheard sounds, but shadows of our own making, places where life itself quietly fades away. These are known as oxygen dead zones, vast stretches of water where the very breath of the sea has been stolen, leaving behind a ghostly void. Fish, crabs, and squid all flee or perish, their bodies sinking into a silent, suffocating stillness. What remains are only the smallest and hardiest of microbes, clinging on in conditions where oxygen has vanished almost completely. The ocean is alive with motion. Currents stir its layers, and waves mix life-giving oxygen into the water. But in certain regions, this balance collapses. When nutrient-rich runoff from agricultural fertilizers and city waste pours from rivers into the sea, it acts as a super fertilizer for algae. At first, the water may seem more alive than ever, teeming with a deceptive green bloom of plankton under the sunlight. It is a false spring. Yet, as this massive bloom of algae dies, it sinks into deeper layers where bacteria begin the work of decomposition. That process is voracious, consuming oxygen, stripping it from the water until little remains. The larger animals suffocate, and the sea becomes strangely, unnervingly still. These zones can span immense distances. In the Gulf of Mexico, one dead zone often grows each summer to cover an area as large as some countries. Similar regions appear off the coasts of India, in the Baltic Sea, and around the world, spreading like a slow contagion. Climate change adds another layer of strain. As surface waters warm, they become lighter, forming a stable layer that resists mixing with the cooler, denser waters below. Without this mixing, oxygen cannot reach the deeper parts, and the suffocating conditions spread further. To dive into these waters is unsettling. Where life usually thrives, a profound silence takes its place, as though the sea itself has been muted. These dead zones are not just a loss of life, they are a chemical shadow we cast upon the waters. And as we drift from them, we find another kind of shadow waiting, not from a lack of oxygen, but from the presence of something that should never have been there at all. The deep ocean has long been imagined as a place beyond human reach, a pristine wilderness untouched by the noise and chaos of our world. Yet, when scientists began sending robotic explorers into the world's deepest chasms, what they found was our own reflection staring back at them. Even in the Mariana Trench, more than 10 kilometers beneath the waves, they found plastic. A simple plastic bag, tangled in sediments, a ghostly monument to a throwaway culture, resting in a place more remote than the moon. It was a discovery that was both heartbreaking and profound. These fragments are called microplastics, tiny particles less than 5 millimeters across, that form when larger pieces break apart under sunlight and waves. Carried by currents, they drift across the seas, a synthetic plankton, sinking slowly until they scatter across the deepest valleys of the planet. What makes this so striking is not just where the plastic has ended up, but how it moves through living things. Deep-sea amphipods, small, shrimp-like creatures collected from the Mariana Trench, were found to have ingested microplastic fibers, their translucent bodies carrying threads of polyester that likely came from a fleece jacket washed in a machine thousands of miles away. This means that plastic is not just settling into the seabed, it is flowing through the very systems that sustain life, from the smallest plankton to the greatest whales. Scientists estimate that billions of tons of plastic have been produced, and much of it has ended up in the sea. In some places, sediment cores, pulled from the seabed, reveal layers rich with plastic fibers, a new and permanent geological marker of our time. Future civilizations, if they study these rocks, will find the signature of our age written in polymers. And yet, despite the weight of this knowledge, there is also resilience. Life in the deep continues. Some microbes have been discovered that can break down certain types of plastic, a tiny, slow echo of nature's endless capacity to respond. Still, the image lingers. The darkest, most remote places on Earth, long thought beyond human touch, now marked by the indelible signature of our waste. We are not only discovering the mysteries of the ocean, we are uncovering our own reflection in it, a reflection scattered in fragments that now belong to the fabric of the deep, beneath the restless surface of the sea, hidden from casual view. A slow and powerful current moves water around the globe. It is often called the ocean conveyor belt, a name that captures both its steadiness and its colossal scale, but it is more than a simple machine. It is the planet's circulatory system, a beating heart of salt and water that moves on timescales of centuries, carrying heat, salt, and the very breath of life across vast distances. It connects every ocean basin into one global system, linking the tropics to the poles and the sunlit surface to the silent abyss. The journey begins in the warm, sun-drenched waters near the equator. Here, the ocean absorbs the sun's energy, and steady trade winds push the surface waters in great, warm rivers like the Gulf Stream. This ribbon of warm, salty water flows northward along the coast of North America, carrying the heat of the tropics into the North Atlantic. As it travels, it releases that warmth into the air like a great radiator, softening winters in Europe and shaping weather patterns across continents. Without it, much of the northern hemisphere would be locked in a far harsher, deeper cold. But as this water reaches the far north, in places like the Labrador and Nordic seas, its story changes. Here, it is met by frigid Arctic winds. It cools, and as sea ice forms, the salt is left behind in the remaining water, making it increasingly dense. This cold, salty water becomes heavy, so dense that it sinks to the deep, plunging thousands of meters into the abyss in what are known as deep water formation zones. This sinking is one of the great engines that drives the conveyor, pulling more warm water northward to replace it while pushing a new, cold current into the deep. This is thermohaline circulation, a process driven by heat thermo and salt haline. The deep currents then flow south, a slow, dark river carrying chill and nutrients toward the other end of the world. Here, it meets the heart of the polar seas, the Southern Ocean, which circles Antarctica in a current so powerful it connects all other oceans together. This is the Antarctic Circumpolar Current, the only current that flows around the entire planet, unbroken by land. It acts as a great mixing chamber, a highway for nutrients and life that distributes the deep, cold water into the Indian and Pacific Oceans, where it eventually rises again, hundreds or even thousands of years after it first sank. The conveyor belt is not only about temperature. It is also the reason the deep ocean is supplied with oxygen and the surface with life-giving nutrients. As waters sink at the poles, they carry dissolved oxygen from the atmosphere into the deep. As they rise again in distant upwelling zones, they bring with them the dissolved remains of countless organisms that have fallen from the surface, delivering a rich fertilizer of nitrates and phosphates to fuel new blooms of phytoplankton. In this way, the conveyor stitches together the entire ocean into one continuous cycle of renewal. But this elegant, planetary-scale system is fragile. Climate change threatens to disrupt the delicate balance that keeps it moving. As glaciers and ice sheets melt in Greenland and Antarctica, they release vast amounts of fresh water into the sea. Fresh water is lighter than salty water, and when too much of it enters the northern seas, it dilutes the very saltiness that makes the water heavy enough to sink. If the sinking slows or stops, the entire conveyor can weaken. Already, Studies suggest that the Atlantic portion of this system is slowing down, perhaps at its weakest point in more than 1,000 years. The consequences of such a disruption would reach far beyond the ocean, triggering a cascade of climatic shifts. A weakened Gulf Stream could mean harsher winters in Europe and stronger hurricanes in the Atlantic. Shifting rainfall patterns could threaten agriculture for billions of people. The polar seas, these frozen frontiers, are the regulators of this system. They are places both fragile and immense, where the line between sea and land blurs into frozen landscapes. The ice itself is a habitat, and the cold, dense waters born here are the lifeblood of the deep ocean. Understanding these currents is one of the great challenges of modern science. Satellites can trace surface waters, but the deep parts of the conveyor remain almost invisible. We map the stars with greater clarity than we trace these slow rivers of the deep. Yet they are the hidden architecture of climate, the silent, beating heart that binds weather, ecosystems, and life itself into one connected web. The ocean does not only hide unknown creatures and landscapes, it also holds memory. Beneath its waves lies the greatest library on Earth, an archive written not in books or digital code, but in the quiet, patient layering of sediment and the silent settling of history. Its collection is vast, holding both the forgotten stories of our own kind and the epic tale of the planet itself, stretching back into a time before we existed. The most accessible chapters are our own. Thousands of shipwrecks rest on the seafloor, their wooden frames and iron hulls slowly consumed by salt and time. Each wreck is a frozen moment, a sudden, violent pause in the flow of human ambition. In the deep, cold waters of the Baltic, the great Swedish warship Vasa was preserved for over 300 years, its ornate carvings and mighty cannons almost perfectly intact. In the Mediterranean, the sea conceals the galleys of ancient empires, Roman vessels that once carried wine, olive oil, and marble across the trade routes that bound nations together. Amphorae, their curved shapes as familiar as pottery dug from land, still lie scattered across the seabed, their contents long gone, but their forms a tangible link to the daily lives of people who lived 2,000 years ago. Historians estimate there may be more than 3 million wrecks still resting beneath the oceans, from the mighty warships of the Spanish Armada to the humble merchant ships lost to storms. It is not only ships that rest beneath the surface. Entire cities have been claimed by the sea. Off the coast of Greece lies Pavlopetri, the oldest known submerged city, dating back more than 5,000 years. Streets, courtyards, and building foundations are still visible, a ghost city on the seafloor. Further south, off the coast of Egypt, the great port of Heraklion was swallowed by the Mediterranean more than 1,000 years ago. Divers have uncovered colossal statues of gods and pharaohs, toppled and resting in the silt, their stone eyes staring into the green gloom. These underwater ruins blur the line between myth and reality, turning whispered legends into archaeological sites. But this human history, as vast as it is, forms only the most recent entries in the ocean's library. Beneath these wrecks and ruins lie older, deeper stories written in the very mud of the seafloor. Every grain of sand, every particle of dust carried on the wind, every delicate shell of a tiny creature that dies in the sunlit waters above, eventually sinks. Over millennia, these fragments compress into thin layers, one resting on top of another, forming pages in a vast geological diary. When scientists drill down and pull up core samples, they are pulling out time capsules. A single tube of mud may hold hundreds of thousands of years of history. Within those fine bands of sediment are microscopic fossils of foraminifera, whose coiled shells hold a precise chemical record of the temperature and acidity of the ocean in which they lived. Layers of volcanic ash mark the dates of great eruptions that darkened the skies, and in a thin, dark line found in sediments around the world lies a spike of iridium, the unmistakable signature of the asteroid impact that ended the reign of the dinosaurs 66 million years ago. These records stretch further back in time than any human document, offering insights into a world we never saw. Yet this library is fragile. Human activity, from deep-sea trawling to the looming threat of mining, threatens to disturb these sediments on a scale never seen before. What took millions of years for the ocean to record can be erased in moments by the drag of a machine across the seafloor. The ocean's lost history reminds us that the sea is not only a wilderness of unknown life, it is also a library of memory. Every wreck, every sunken street, and every layer of sediment is a page of a book too vast for us to ever finish. Yet with each core sample and each dive, another fragment is brought back into the light. Another story recovered from the silent, patient deep. For all the brilliance of modern science, for all the rockets we have sent into orbit and the probes we have flung toward the edges of the solar system, our ability to explore the ocean remains astonishingly limited. The technology we have, powerful as it may seem, struggles against the sheer scale and hostility of the deep. It is a realm that seems actively to resist our intrusion, a place where our most advanced machines falter when faced with the crushing pressures, the vast distances, and the unforgiving nature of the sea. Human-occupied submarines, or HOVs, are perhaps the most iconic tools we possess for visiting the depths. They are marvels of engineering, capsules of titanium and steel, wrapped in walls thicker than the vaults that guard our greatest treasures. Yet, their strength comes at a steep cost. Each descent is a monumental undertaking, expensive and dangerous, requiring vast amounts of preparation, specialized crews, and massive surface ships to support them. A single dive that lasts only a few hours may require months, or even years, of planning. As a result, manned exploration of the deepest ocean is exceedingly rare, a privilege reserved for only the most determined scientists or the wealthiest adventurers willing to risk it all for a glimpse of the abyss. To extend our reach, we send machines where humans cannot, or dare not, go. Remotely operated vehicles, or ROVs, glide through the dark, our eyes and hands in the abyss. They are tethered to ships on the surface by thick cables that provide power and send back streams of data and haunting images of landscapes never before seen. Yet, that very tether is their greatest vulnerability. It is a lifeline that can snap under stress, become snagged on unseen rock formations, or be dragged by powerful, unknown currents. The intense pressure can warp their housings, and many have been lost to the depths, vanishing into places where no recovery is possible. The next generation of explorers are AUVs, autonomous underwater vehicles. These are untethered, pre-programmed robotic submarines that can roam freely, mapping the seafloor or collecting data over vast areas. But their freedom comes with its own challenges. In the deep ocean, they are deaf and blind to our primary mode of navigation, GPS. Radio signals cannot penetrate the water. Instead, they must find their own way using inertial guidance systems and sonar, a far less precise method. Their missions are a constant race against time as their batteries drain quickly in the cold. And if one fails to return to its rendezvous point, it is simply lost forever, its precious data sinking with it into the silent mud. Even if our machines were perfect, we would still be faced with the staggering, mathematical impossibility of the task. The ocean is simply too big. Mapping the entire global seabed with modern, high-resolution sonar would, by some estimates, take a single ship more than 200 years to complete. Even with a fleet of 10 ships working non-stop, the task would take decades. To put it in perspective, it would be like trying to survey the entire surface of the Earth, land and sea combined, using a single flashlight on a moonless night. This is where the contrast with space exploration becomes so sharp. The great observatories we have sent into orbit can capture images of entire galaxies in a single exposure. But the ocean grants us no such sweeping vistas. It forces us to learn about it one narrow strip at a time. And this brings us to the most human of all barriers, priority. Each year, nations pour billions upon billions of dollars into the exploration of space. It is a grand, romantic endeavor that captures the public imagination. Space offers us spectacle, the fiery drama of a rocket launch, the crystalline images of distant nebulae, the dream of walking on other worlds. The ocean, by contrast, offers us darkness and silence. Its exploration is slow, methodical, and largely invisible. It does not dazzle in the same way, and because of this, the urgency, the funding, and the political will to explore it have always been a pale shadow of their celestial counterparts. The irony is that the deep ocean is in many ways more alien than the moon, and its discoveries have a far more immediate impact on our lives. Yet the imbalance continues. Rockets soar while research ships rust in port. Telescopes gaze at distant galaxies, while the living world a few kilometers beneath the waves remains less understood than the barren plains of Mars. It is this combination of hostile physics, immense scale, technological limits, and a fundamental failure of human priority that makes the deep sea our truly impossible frontier. Part 15. The final question. As we imagine what might come next, fleets of autonomous submarines, guided by artificial intelligence, mapping the abyss in silent swarms, or industrial machines descending to mine the seafloor for precious minerals, a quiet but persistent question lingers. It is a question that hangs behind every expedition, every blueprint for a new submersible, every dream of charting the last hidden corners of the Earth. Should we explore everything? The drive to know is deeply, fundamentally human. It has carried us across deserts, over mountains, and into the vacuum of space. Yet the ocean presents not only a challenge of scale and technology, but also a challenge of philosophy. In the dark, silent waters, where so much life has evolved unseen, the act of discovery and the act of destruction may come hand in hand. When we think of the unknown, it is easy to imagine it as a blank canvas waiting for us to paint a picture upon it. But the ocean is not a canvas. It is a living system, ancient and fragile, in places untouched for millions of years. Ecosystems have formed that depend on delicate balances of chemistry, pressure, and silence. The slightest disruption, the roar of a motor, the heat of a lamp, the chemical trace of a machine, or the scrape of a drill could alter those balances in ways that cannot be undone. To open every door is to risk shattering what has survived in the dark without us for eons. This creates an ethical dilemma. On one side lies our insatiable curiosity, the urge to see, to know, to expand the boundaries of our understanding. On the other side lies restraint, the quiet wisdom that recognizes that knowledge gained too hastily may cost more than it offers. Some scientists and philosophers argue that mystery itself is a form of protection. By leaving certain parts of the ocean untouched, we grant them a kind of sovereignty, safeguarding them from our interference, from exploitation, and from the unintended consequences that follow our presence everywhere we go. The question then becomes not whether we can explore, but whether we should. We often treat exploration as a conquest, a way to extend human presence into places that existed long before us. Yet the ocean does not need us. Its memory is recorded in sediments. Its creatures adapt to crushing pressures. Its cycles continue endlessly. Our presence is the anomaly, not the constant. At the same time, withholding exploration is not simple. Knowledge of ocean currents helps predict devastating storms. Studies of deep-sea microbes may lead to medicines that save countless lives. To turn away from the unknown is also to turn away from potential solutions to our greatest problems. The challenge lies in finding a balance, in pursuing knowledge with a gentle hand, in learning to be guests in a world that is not our own. Perhaps the greatest lesson the ocean offers is humility. For all our satellites and submarines, for all our ambition and ingenuity, we remain small against its immensity. The unknown is not a void waiting to be filled. It is a mirror, reflecting our own limits. The decision to explore or not to explore is also the decision of what kind of species we choose to be, one that consumes every mystery until nothing is left hidden, or one that can allow some secrets to remain, held safely in the dark. For all our progress, the ocean still holds more mystery than any frontier we have ever faced. It is not just a place on Earth, but a reminder that some wonders will always outpace our reach. The sea continues to hold stories older than humanity, written in sediments and whispered through currents. It is both a cradle of life and a vast abyss, both a source of sustenance and a realm of profound silence. As this journey through its depths draws to a close, it becomes clear that exploration is not about conquering, but about listening. Every ghost sound recorded on hydrophones, every flicker of bioluminescent light, every glimpse of a strange new creature is the ocean speaking in fragments. We can gather those fragments, but the whole will always remain larger than the sum of what we can hold. That truth is not a failure, but a gift. It means the ocean will always have more to give, more to show, and more to teach us about the scale of life and of time itself. If you have found yourself carried by this journey, I invite you to join me again in the future as together we wander gently through the mysteries of science. A simple like, a soft tap of subscribe helps this little corner of curiosity reach others who may be searching for wonder in the quiet of their night. And if you would be so kind, share your thoughts in the comments. What do you think lingers in the deep? What secrets of the sea feel most haunting to you? Every voice adds to the conversation, just as every drop adds to the ocean. It is always a joy to see where you are listening from and at what hour of the night or morning you drift into these stories. Now, the sea will go on, endless and unknowable, and we will carry its mystery with us. For though we dream of exploring every corner, of pulling back every shadow, the ocean will always remain vaster than our reach, deeper than our tools, and darker than our imagination. It is, and will always be, Earth's greatest frontier.